So this is dealing with what I call conservation of energy, and conservation of energy in this context is an umbrella that covers conservation of mechanical energy. But this is not about conservation of mechanical energy necessarily. Do you agree that work is a type of energy? Type is maybe the wrong word. Do you agree that work is energy? So if work is done, I can still use the concept of conservation of energy. Is heat energy? Yes, it's not mechanical, so I can always use conservation of energy. We're going to be solving problems today dealing with conservation of mechanical energy, conservation of energy in general, and what's called the work energy theorem, which sounds fancy, but it's not. It's really basic. So just to review, what are the two conditions that can exist if mechanical energy is not conserved? I'll remind you that mechanical energy is conserved if the kinetic and the potential energy at one point are equal to, when you add them together, are equal to the total mechanical energy afterwards. The kinetic and potential after, added together, give you the same as the kinetic and potential energy before. When is that not the case? What's one situation that can arise if mechanical energy is not conserved, Ephraim? Right. And when we say when work is done, let's make things simple for ourselves and say work is done in a positive fashion. You're adding energy to the system. Is work done when you slow down and stop an object? Yes. But when we say work is done, typically we mean work is added, or energy is added. So when work is done, the final EP plus EK is different than the initial EP plus EK. And I just said, let's make things simple for ourselves by talking about a positive amount of work. I rescind that statement. If you are doing a positive amount of work, and remember, work is a scalar. I'm not saying there's a direction associated with it, with that positive. When I say work is positive, you're adding energy to the system. Let's not forget the definition of work is a change in energy. So if you do work, you change the energy in the system. If you're doing a positive amount of work, then the energy in the system goes up. If you're doing a negative amount of work because you accomplish it by applying a force backwards to the motion, then the amount of energy goes down. In either case, you're changing the amount of mechanical energy in the system. What's the second situation that can arise where mechanical energy is not conserved? So let's just say no work is done. Can you come up with a reason why the mechanical energy would not be conserved, even though you're hands off, you're not touching the system, you're not doing work? Why would that be? Colin? Do you know? That's okay. Superman? Friction. Now, friction is a force. So what effect does a force of friction have on energy? Where does the energy go? Heat energy. Okay, so, and I just want to just tie that up in a nice bow rather than just saying friction. If a force of friction exists, heat energy will be produced. Where does it come from? Well, it has to come from somewhere. It comes from bleeding out of the kinetic and potential energy in the system. Some of that kinetic and potential energy get lost to heat energy. So when a frictional force acts to produce heat energy, and well, I'll give you a second to write that down. I have something that I want to say, but it requires attention in terms of you listening to it. For part A here, I said when work is done, the final potential and kinetic, the final mechanical is different. When work is done, can the final kinetic and potential be more than the initial? Yes. Can it be less than the initial? Yes. Because you can apply a force in the opposite direction to the motion, bleeding away some of that kinetic energy, let's just say, decreasing the mechanical energy in the system. Okay? However, when a force of friction acts to produce heat, the fact of the matter is that EP final plus EK final must be smaller than the initial. You can't produce heat and get more energy in the system afterwards. That energy dissipates. The word we use is dissipates. It dissipates into the environment, heating up the air and the surfaces. Oops. Okay. So when work is done, you can do a positive amount of work or you can do a negative amount of work. When friction acts, the fact of the matter is it will always decrease the mechanical energy in the system. You can't turn heat into mechanical energy. That's not how it works. If there is a force of friction, that force is what we call a non-conservative force because it produces heat energy. Okay? If it's a conservative force, then no heat energy will be produced. And I've already said this, but when heat energy is produced, the mechanical energy decreases. So energy is conserved, it's just not mechanical energy. Okay? The last example that we did on Thursday had a ball rolling down a ramp or something sliding down a ramp. And we calculated the potential energy at the top and we calculated the kinetic at the bottom. Let's just say, because I don't feel like pulling up those numbers, that we had a ramp and we had a box on the ramp and we determined, and it starts from rest, we determined that the potential energy at the top was 100 joules. And then at the bottom, where it has a height of 0, we determined the kinetic energy was 40 joules. Are you with me? What's its kinetic energy at the top? 0, right? So EK here at the top is 0. Let me move these over here. And what is EP here? EP here is 0. What's the mechanical energy at the top? Well, 100 joules. What's the mechanical at the bottom? 40 joules. Yes? Is mechanical energy conserved? No. Why? Well, because as this slides down the ramp to get to the bottom, I'll just draw it there, there's this heat produced. And the heat is warming the surface of the box and the ramp, and then it goes out into the air through collisions with molecules and all this bit of business. But there must have been 60 joules of heat. Would you agree on the math there? Okay. So is mechanical energy conserved? No. Is energy conserved? Yes. Energy is conserved. It's just not all mechanical. If you take the initial energy of 100 joules, bless you, and the final energy of 40 joules plus that energy of 60 joules, which is there at the end. It happens gradually over time, but when the box is at the bottom, that heat energy is in the environment. The total energy afterwards is still 100. So that's what I'm talking about here. Now we have to learn something, though, about how to calculate heat energy. This is really, I think, one of the only new things today. A force of friction results in heat energy. In other words, the mechanical energy before is the mechanical energy after plus the heat energy. That's not the new thing. We calculate the heat energy using this formula, which is not on your formula sheet. Why do you take the force of friction times the displacement to get heat? Because heat is the work done by friction. If you want to know the work done by my puppy, when I'm gardening in the summer, I strap a big wagon to my puppy so that I fill it with dirt and Panda moves around and does work for me. I don't do that. But if I want to know the work done by Panda, that's my puppy, in pulling a wagon, then I have to take the force that she applies times the displacement. If I want to know the work done by me, I take the force that I apply. Work is applied force times distance. So the work done by friction, which is heat, is the applied force of friction times the distance. If work is done to a system, we change the amount of energy in the system, and this is called the work energy theorem, a real sophisticated sounding thing, which is just that. It's the definition of work. This is actually on your formula sheet. It's an idea, it's a physics principle, but it is on your formula sheet. It says work equals delta E. And delta is final minus initial. If no work is done and there's no heat, we're back to Thursday's topic where this is what we do. So essentially, as we solve the problems we're going to be working on today, we ask ourselves this. Work done? If yes, we use this idea. Heat produced? If so, we use this idea. No work, no heat. This is what I've meant all along whenever I say Physics 20 is not about formula. Well, it uses formulas, but it's not about which formula do I use to solve a problem. Well, we've got 3 different formulas there. None of them are on your formula sheet. And each one of them can be customized further depending on the situation. You're with me that this is collectively initial and this is collectively final. Once you wrap your head around that, this doesn't have to be difficult. Determine the amount of work done in stopping a 250,000 kilogram train that's traveling at 70 kilometers per hour. So when we go from having the train moving to having the train not moving, I hope it's clear mechanical energy is not conserved. What's done then is work. It's done by the application of a force resulting in a, quote, deceleration. What's interesting here is if you want to try to solve this with kinematics and dynamics, you can't do it. You can't solve this by going force times distance. You don't know the distance. The force is the net force, which happens to be a force of friction. You have no access to any of this information because you don't, VI and VF, but that's it. So what we do instead is we say, well, it's the work energy theorem because work is change in energy and you're doing work to change the energy of the car. Train. So this is the final energy minus the initial energy. Are we going to assume that this train is coming to a stop on a ramp? No. We're going to assume it's on a horizontal surface, which means potential energy doesn't fit in here. This is all about kinetic energy. The initial energy is kinetic, and we can say the final is kinetic, but really the final is going to be 0. all we have to do is calculate the kinetic energy that the train had to begin with and see if you follow this without use of a formula. If you know the kinetic energy of the train to begin with and it stops, then it has lost all of its energy, so that energy is really kind of the amount of work you've done. You do have to convert that 70 kilometers per hour to meters per second, which is 19.4, repeating, meters per second. I think we've come far enough together that we don't need to write all of these numbers down every time we do a question like this. I'm getting this amount of energy. Now it's negative. I forgot the negative. Does anybody else get that number? So negative 4.7 times 10 to the 7 joules. I want to just quickly go through something with you. Are we okay with that example? Let's say everybody, that the distance it took to stop was 1,000 meters. Okay? Could you have solved this knowing that using force times distance? Yes. This would be the force of friction between all the moving parts in the tracks in stopping the train, which it would be the net force, because that's the only force. Once you add together the force of gravity and the normal force, all you're left with is that backwards force of friction, which would mean this would be ma times d, and you could calculate the acceleration with this formula. I'm not saying do it this way. I want to demonstrate something to you. So if I do that, I have to take vi squared, subtract it to the other side, and divide by 2d, which is 2,000 meters. And this would be the acceleration. And it's a negative acceleration. The size of that number tells me the train could certainly stop in less distance than 1,000 meters. Okay? Because I don't think that's really that, well, maybe that is the acceleration of a stopping train. I don't know. You don't want the acceleration to be 5 g's, do you? Okay. So now what I can do is I can take the mass, multiply by that acceleration, and multiply by 1,000 meters. You get the exact same answer. And if I used 100 meters, you get the same answer. And this has to do with the conversation we had, that over here, when you're taking that formula to find the acceleration, you end up dividing by the distance at some point. But in this equation, you end up taking your acceleration that you found by dividing by a distance, and you multiply by the same distance, so it doesn't matter. Let's take a look at another one. 15-gram arrow is pulled back 45 centimeters in a bow by exerting an average horizontal force of 65 newtons. How fast will the arrow leave the bow at? There are different ways that you can approach this, but this is a classic question where what you say is that the bow is going to do work to the arrow. When I'm holding the bow and arrow in this position, in the drawn position, I'm going to let it go and the arrow will accelerate, gaining mechanical energy. Correct? Why is the energy of the arrow increasing? Because the bow is doing work to the arrow. So what we do here is we say work equals delta E. And in this case, I think it's very valuable for you to write by the bow of the arrow. So what I'm saying is that the bow is the thing doing the work. The thing changing its energy is the arrow. In other words, the bow is doing work to the arrow. What kind of energy does the arrow get? Kinetic, right? And that means that we can say FD equals the change in the kinetic energy of the arrow. So we're building an equation. Work is force times displacement. Now, there's a subtlety here that in the past I wouldn't even talk about. But I like to challenge my students to think about this. This has to be the force that the bow applies to the arrow. That force of 65 newtons is the force that you apply on average to the bow. But that means, based on Hooke's law, that force that you apply is the elastic force forward when I release it. So if it takes me an average force of 65 newtons to draw the bow to that point, when I release it, the average force, forget about releasing it, at that point, the force forward on the bow is what I've applied. So when I release it, that force gets used against the arrow. Very simple question, by the way. 0. So this is going to be 65 newtons multiplied by 0.45 meters equals 1/2 times the mass of the arrow in kilograms times v squared. I don't know if anybody remembers, but let me just calculate the work done. I think it was Thursday. I said, taking an energy, which is what this 29.25 is, and finding a speed is a calculation you will do at least 100 times in Physics 30. I'm saying that to try to implant that into your brain, that you take the energy times 2, divided by the mass, take the square root. So I'm multiplying by 2 to get rid of that half, and then I divide by 0.015, and then I take the square root. So it's about 62 meters per second. About 200 kilometers per hour, a little bit more. We times that by 3.6. About 225 kilometers per hour. I take a 2-kilogram rock, and it's at some point right here. Now, when you throw an object in the air, do I just kind of blink or something and it's all of a sudden moving? No, what I have to do is I have to apply a force. I'm not going to throw this, but if I started to throw this from here, I have to apply a force and move it vertically and then let it go, and it will be moving, right? So, do I do work to this rock? Yes, because you have to apply a force to the rock over a displacement. You're doing work. So right away, this is where we head. We go work done by me equals change in energy of the rock. This is the force times the displacement. And this is, well, would you agree it's the mechanical energy afterwards minus the mechanical energy before? Yes? I hope you'd further agree that this is zero. I'm not saying you're throwing it from the ground. I'm saying that wherever you start applying the force, you're going to call that zero to make your life easy. And you're not on a jetpack moving through the air while you're throwing it. So the rock starts from rest to begin with. But my question now becomes, what kind of mechanical energy does the rock have at the end of this application of the force? There's only two types of mechanical energy, potential or kinetic. And by the way, there's no elastic here, so there's no elastic potential energy. So we've got gravitational potential energy and we have kinetic energy. I'm asking, what kind of mechanical energy does the rock have when I let it go? It's both. And most people will just say kinetic energy because it's moving. But you are at a taller distance. You are at a greater height than you were to begin with. So if the rock starts here, and this is where your hand is holding it, this is your hand, and you're clenched around it, and then up here you release your fingers and let it go, so V is 0 here, there's no kinetic, H is 0, there's no potential. But it's moving here, so it has kinetic, and it also has potential. So this is going to be 1/2 mv squared plus mgh. There is an end eventually to the numbers of different equations we can develop. But this is an equation we haven't seen before. Every situation can potentially produce a new result. I mean, sooner or later you'll do enough of them that you'll start to see the same thing again. So now we can put the numbers in. 35, 2, and 1. 35 newtons times 1 meter equals 1/2 times 2 kilograms times v squared plus 2 kilograms times 9.81 times 1 meter. This is just a number. This is just a number of v squareds. This is just a number. So if you want to find out what v is, you have to subtract the numbers to the other side and then divide by the coefficient of v squared. But this is 35. That's v squared. Can you double check my arithmetic? Pretty sure that's right. I mean, we kind of caught a lucky break here that the mass of the rock is 2 kilograms and it's 1/2 times 2, which is just 1. Then times v squared. So v squared will equal, I want to say 15.38. Pretty sure. Take the square root, you're going to get just a little bit under 4 meters per second. 3.9. You okay with that? Number 4, a 20 kilogram box slides down the ramp shown from the top. There's a force of friction. Okay, well, right away there's a force of friction. Heat will be produced. Is work done? No. It doesn't say, and somebody's pulling on the box with a rope or pushing with their hands. And that means that the energy in the system before and the energy in the system after are equal. No work is done. You cannot change the total energy unless you do work. The difference here is this is not mechanical energy that's conserved. It's going to be the potential plus the kinetic to begin with will be equal to the potential plus the kinetic afterwards plus heat. Why am I allowed to do this? I guess the question is flawed. It should say it's released from rest. Why am I allowed to do this? Because we make the wise move of saying that this is where h equals 0. I hope it's obvious that for this thing, we're going to need to know this height. So can you use, I guess, the Pythagorean theorem to find that height? I want to say 6 meters. 10 squared minus 8 squared, and then take the square root. There's one more thing, though. This is MGH. We know that. In fact, I think some of you might be able to do the problem without actually writing MGH. You know that's how you're going to calculate that. This is 1/2 mv squared. What is heat? I mean, how do you calculate heat? Well, heat is the work done by a force of friction. Work done is the force applied times the distance. We want to be very careful here that this is h over here. But this is d. Right? Potential energy is measured relative to a vertical height or using a vertical height. The distance or displacement of the box is the distance over which the force of friction was truly acting, and it was over 10 meters. Can I cancel the masses? No, because there's no mass in that force of friction times displacement. So what do we got here? 20, 55. 20 kilograms times 9.81 times 6 meters equals 1/2 times 20 plus the force of friction times 10. And just because, oh, forgot my v squared there. I'm going to show intermediate steps here. So when you calculate the potential energy the box has at the top, you get approximately 1180 joules, approximately. When you calculate the amount of heat produced, you get 550 joules. So mathematically, to get the kinetic energy, you subtract these numbers, but physically, it should make sense to you that you take the energy it had to begin with and you take the heat out of it, and you're left with the kinetic. So when I subtract this, that's 450, 550, 627.2. Anybody want to either confirm or correct me on that? That's correct. That's the joules of the potential minus the heat, which is the joules of the kinetic energy. So we can divide that by 10 and take the square root. about 7.9 meters per second. And there's one more example, I think, but I don't think we'll do it. I just want to set it up. This example is here not because you're going to see stuff like this on an exam or even necessarily on an assignment, although that might be possible. It's because, as I've said before, many of you will go on and enroll in engineering programs and other science and math programs where you might do something like this. So I just want to set this up and then we can get to work on some problems. 120 Newton force is applied to a box. Are you doing work? Work is done. If work is done, there is no question about it that you have to, well, there's other ways to weasel and maneuver your way around it, but you have to basically consider work as change in energy. Does the box gain kinetic energy? Yes. Does the box gain potential energy? No, it's on a horizontal surface. So what you would normally do is say the work done, which is force times displacement, is the final kinetic energy minus the initial kinetic energy. But what other type of energy is present at the end? And frictional energy is not a thing. Heat energy is present at the end. Because you're told there's a force of friction. And what that means is that another part of the energy at the end is this. This is the final energy. This is a problem, by the way, you could solve by using a free body diagram and kinematics and dynamics. And that's how you would solve this problem. It would become really a beast because this is going to be the force of friction times, no, this is going to be the force applied times the distance equals 1/2 mvf squared plus the force of friction times the distance minus 1/2 mvi squared. Like there's a lot going on there. I don't think the understanding of everything I've just talked about is beyond anybody in this room. The fact of the matter is, if I gave this on an exam, a lot of you would not be able to get it right because there's just too many steps, even though you understand it. I could make it more complicated and say that this is also happening while I'm pushing it up a ramp, which would mean there's also mgh at the end. I wouldn't do that. But you might see that in an introductory physics course in university. Your goal here, just one final time, is to ask yourself if mechanical energy is conserved. And this is, if you turn the page on your handout, I think. No, it's not there? Oh, it's at the bottom of page 42? Okay. This is in your handout. There's no need to copy it down. If you know that no work is done and no friction acts, then this is what's going on. If these sigmas bother you, they just mean total, then don't worry about it. If no work is done and no friction acts, then no heat is produced, mechanical energy is conserved. If work is done, then you use the work energy theorem and you say work equals final energy minus initial energy. If friction acts, then total energy to begin with equals total energy afterwards. It's just that thermal energy or heat is produced afterwards, and this is found by taking the force of friction times the displacement. I hope it's obvious. These two F's mean something different. One is for final, one is for friction.